Diphtheria is a contagious bacterial infection caused by the bacterium Corynebacterium diphtheriae that, when infected by bacteriophage, produces a toxin that causes the most serious results of diphtheria, such as the preclusion of the process of protein synthesis, preventing the production of proteins in cells. This toxin consists of two polypeptide chains, fragment A and fragment B. Fragment B acting as a recognition subunit, gaining the toxin entry to the host cell, where the disulfide bond joining the two fragments dissolves due to the acidity of the endosome, also causing fragment B to create pores in the endosome membrane, catalyzing the release of fragment A into the cell's cytoplasm. Fragment A then acts to inhibit the synthesization of new proteins in the affected cell through the catalyzation of ADP ribosylation of elongation factor EF2, a protein necessary in the translation step of the protein synthesis, with EF2 being essential in the transportation of tRNA from the A side to the P side of the ribosome during protein translation. This toxin can incur further drastic effects in the form of destruction of tissue at the site of infection, the formation of the characteristic membrane, and the inflammation of the heart and nerve damage. The presence of diphtheria is identifiable through distinctive symptoms, with the most visible and common being the formation of a membrane in the form of a thick, grey coating on the throat and tonsils, with other common symptoms being the presence of a fever, chills, swelling of the lymph nodes in the neck, a barking cough, a sore throat, and a bluish tint of the skin, with the progression of the infection presenting symptoms of difficulty breathing or swallowing, changes in vision, slurred speech, signs of shock such as pale and cold skin, sweating, and rapid heartbeat. This bacterial infection is transmitted through human-to-human contact. Typically, this human-to-human transmission of diphtheria occurs through the air, when the new host breathes in particles expelled during a sneeze or a cough of an infected person. The human-to-human transmission of diphtheria virus may also occur if an uninfected person makes contact with the skin lesions of an afflicted person. However, this is uncommon. Indirect transmissions of diphtheria virus may also occur if an infected individual makes contact with a surface or object, as the bacteria can be left behind, remaining viable to infect a non-afflicted person. The introduction of the diphtheria virus through the chemical and physical barriers of this body elicits an immediate immune response through recognition of the foreign antibodies. This response is first evident in the innate immune response, with macrophages in the tissue engaging in phagocytosis with the pathogen and secretes cytokines and chemokines, in order to induce an inflammatory response, in order to draw more immune cells to the area of infection to avoid any further colonization of bacteria. This is further evident in the T-cell mediated immune response, where although cytotoxic T-cells do not have much effect in the prevention and spread of C. diphtheria, because when fragment A of the exotoxin enters the cytoplasm halting protein synthesis, the cell will die. In order to combat the disease, cytotoxic T-cells recognize viral peptides on a bacterial surface and induce cell death via the membranous attack complex. However, if the cell had already died from toxin, when the cytotoxic T-cell would be unable to inhibit the spread of the disease in any capacity. However, T helper cells help in protectivation of macrophages, which engage in phagocytosis with the pathogen, and the activation of the B cell, allowing for the humoral immune response, where the B cell will split into a plasma cell, which produces antibodies which coat the pathogen and disable it from infecting the host cell, in a process known as neutralization. Furthermore, anti-fragment B antibodies, which attack the B component of the diphtheria toxin, are primary ones responsible for neutralization, since it was the B portion of toxin that produced by diphtheria that adheres to the cell membrane and forms a channel so the toxin can be internalized. If this is blocked by antibodies, then the toxin is not able to properly infect the host cells. Vaccines are vital in the prevention of the spread of such deadly infectious diseases, with vaccines providing artificial mediated diseases through the introduction of cultured microorganisms that are weakened, dead, or altered. These introduced bacteria, while harmless, stimulate the body's immune response in the form of primary response, triggering the helper T cells to secrete interleukin-2 to stimulate the B and T cells into splitting the plasma cells, cytotoxic T cells, and memory B and T cells, specific to the antigen. The other two cells remain in the body for a long time, providing the body with immunity in the form of secondary response. The same antigen re-enters the body and is recognized by the memory cells, stimulating the rapid production of the appropriate B and T cells, with a larger quantity of B cells and subsequent larger amounts of plasma cells and antibodies, allowing for the effective disposal of the virus before it has a chance to manifest in any symptoms or problems. This process is referred to as active acquired immunity, with the body learning how to mount an effective response against the disease through past interactions with antigens in a weakened form. Vaccination programs are markedly the most effective form of prevention of the spread of disease, such as smallpox, polio, diphtheria, with mass immunization programs such as the Expanded Program on Immunization launched by the World Health Organization in 1974, conducting mass vaccinations in communities at risk of outbreaks of diseases, and monitoring for any resurgence of disease within the population, allowing for the vaccinated part of the population, by proximity, the unvaccinated members of the population to be safe from the outbreak of disease. With these public health programs not only being effective in the reduction of the occurrence of disease in individuals, but also having decreased the spread of disease throughout the population. The effectiveness of vaccinations is exemplified through the near eradication of diphtheria, a contagious bacterial infection with a 90% mortality rate for diphtheria of the larynx, with 2/3 of these fatalities being children under the age of 5. This disease, prior to the development and widespread use of the vaccine, caused 206,000 cases, with 15,500 deaths in 1921 in the United States alone. However, with the introduction of the diphtheria vaccination, this figure dropped rapidly, with 32 cases of diphtheria being recorded in the United States between 2004 and 2015. The commonality of the outbreak of diphtheria dropped globally, with the World Health Organization introduction of the EPI in 1974, raising the number from only 5% of children being vaccinated worldwide in 1974 to 8% by 1990, having a corresponding dramatically decreased mortality rate worldwide. These vaccination programs have resulted in the disease being essentially eradicated in developed countries, with the exception of small outbreaks, and the disease remained present in developing countries. The effectiveness of vaccines in the prevention of the spread and occurrence of the disease is further evident in the complete eradication of smallpox virus, a virus responsible for the 10th of the deaths in Europe in the 19th century and 300 million deaths in the 20th century, in spite of the existence of a vaccine developed by Edward Jenner in 1976. However, this number dropped rapidly due to the inception of the Worldwide Immunization Program by WHO in 1967, which aimed to completely eradicate the disease through mass immunization and surveillance and analysis of emerging new occurrences of smallpox worldwide. This goal of the complete eradication of smallpox virus was accomplished over a decade later, with the last known natural occurrence being in Somalia in 1977, and the disease being declared completely eradicated by the World Health Organization in 1980. This effective prevention of the spread and occurrence of disease due to vaccination programs is further apparent in the eradication of the highly contagious poliovirus, a disease which, prior to the introduction and widespread use of the polio vaccine, there was over 590,000 cases of polio, over 800 deaths in the 1930s, 40s, and 50s in Australia alone. However, the incidence of polio outbreaks decreased significantly with the introduction of the EPI in 1974, and decreased further with the WHO introduction of the Global Polio Eradication Initiative in 1998, involving the widespread vaccination of children under 5, especially in countries where the disease was still endemic, reducing the number of cases from 350,000 at the inception of the initiative to 2,700 cases in 2000. This drastic decline in polio infection rates since the creation of the vaccination program demonstrate the effectiveness of such programs in the reduction of the spread and occurrence of such diseases, with the polio virus only resurging in poor and developing countries.